Hello and welcome to lecture number 3 in the course Advanced Robotics. In the last lecture, I discussed about the various joints and using various joints how you can make different kinds of robots. And then we moved on to the transformation matrix, that is the rotation matrix, which relates the coordinates of a point in a rotated system to that of a reference system. Okay, so today we'll start off from there. I'll very quickly revise and then we'll move on to the next part and solve some problems on rotation matrices and homogeneous transformation matrices. Okay, so we are today discussing about transformation matrices, and we saw that we have a robot having multiple links, a serial link manipulator like this, and what we do is we put axis or reference frames in each of the joints. So we define reference frames in each of the joints and then try to find the relation between each of the different frames. Okay, so we are putting frames in all the joints, and then this Z3, and let us say that is Z4, and we have my X2 here, X3, X4. Exactly how to put frames, I will come to it in the next class, but today just assume that these are frames that have been put. Now, when a robot moves, the end effector position and orientation changes, and we want to know the position orientation of the end effector with respect to the base frame. Now this is my base frame, which is 0, 0, 0, which does not move. Okay, so which essentially means that I need to find the relation between respective frames. So what is the relation between this frame and this frame, and from here to here and from here to there we come to the base frame. Now what is the difference between these two frames? We observe that the origins are different. There is one origin here which is at 0, 0, 0, and the origin of frame 4 is here. So it is like the origin of frame 4 has translated by some distance and gone there. Okay, so there is a translation involved. Next is between these two frames, the Z0 frame and the Z4 frame, or the frame 0 and the frame 4, there is some angle between the axis, right? So there is some rotation involved. So there are two transformations that are involved. One is called the rotation transformation, and the other is the translation transformation. Okay, so if you know these two translations, these two operators, then we can move from any frame to any other frame in a three-dimensional space. So in the last class, I had very quickly derived the rotation transformation. So assume that we have an axis, the original, the fixed frame which is not moving, called frame A, is here. So this is my X, Y, and Z, and there is another frame which is rotating with respect to Z. In this case, it is rotating with an angle theta with respect to the Z axis. So this is my frame B. So this is my frame B, and this is X dashed, Y dashed, and Z dashed. Okay, now if there is a point here, the coordinates of the point are specified like this. So we call this point P, and we are defining the coordinates of the point P with reference to a frame. So I say PB is equal to U, V, and W. And similarly, there is a point P which is expressed with reference to frame A as AP, which is defined as XYZ. Now, what does PA means? PA means XYZ is along the axis of A. Okay, so XYZ is with respect to A. So what is X? X is projection here, and Y is there, and Z is in the Z direction. Okay, so this is my X axis, that's my Y axis. Now, what is the meaning of BP? It means the point P, the coordinates of the point P, UVW, are expressed with reference to frame B. So with reference to frame B, this is my U, and that is my V. Okay. So I want to find the relation between the frame. So AP, what is the rotation? What is the matrix which relates the frame, the point P, with expressed with reference to frame A in terms of frame B? Okay. So this is what I want to find out, and this is what is called the rotation matrix. So from geometry, we make this very simple construction here. We find that this angle is theta and this angle is also theta. So I make this construction and see that this is my distance x, and x is equal to, this is u cos theta. This full distance is u cos theta. So this is u, so this full is u cos theta, and this is u sin theta. This is my v. Okay, so this distance is equal to v sin theta, and distance is equal to v cos theta. Okay, so I can geometrically find out x is this distance. X is equal to this full distance, u cos theta minus v sin theta. What is v sin theta? That is this much. So this is equal to v sin theta. Okay, and then similarly y is equal to u sine theta plus v cos theta, and z is equal to w. So in matrix form, when I write this, we write this as x, y, and z. X, y, and z is equal to the rotation matrix cos minus sine, sine cos 0, 0, 1. This is 0, 0, and this is the coordinates expressed in frame B, which is u, v, and w. So this matrix is called the rotation matrix, and this matrix relates the coordinates of a point expressed in a rotated system. So this is expressed in B, in frame B, to that of the reference system, which is in a frame A. And this is a 3 by 3 matrix, and it has several properties we have seen. Some of the properties of this matrix are properties of rotation matrix. We have seen the determinant of R is equal to 1, R transpose is equal to R inverse because it's a proper orthonormal matrix. Then each of the columns x mod of y is equal to mod of z, which is equal to 1, and then x dot y is equal to x dot z is equal to y dot z is equal to 0. Y dot z is equal to 0. Okay. Why is this happening? Essentially, this is happening because the axes are unit vectors and they are 3 orthogonal unit vectors. Okay, that is the reason why these conditions are being held. Okay, so now we have seen that we can find the rotation with respect to any axis. I have derived it with respect to our z theta, where we got cos theta minus sine theta cos theta 0, 0, 1, 0, 0, and we can derive it with respect to our x. Let's call this alpha, rotation about the x-axis by an angle alpha. So this will become 1, 0, 0, 0, 0. So this is cos alpha, sine alpha, cos alpha. Okay, so what you see is that, and the third one is our, let's call it y beta, so rotation about y-axis by an angle beta. So this is 0, 1, 0, 0. This is cos beta, sine beta, cos beta. Now what you see is that when it is rotating about the z-axis, then the z part becomes rotation about z-axis, means this will become 1. This component will become 1. Similarly, when it is rotating about x-axis, this component is 1. This is 0, 0, that's 0, 0. When it's rotating about y, this will become 1. So it basically means the coordinate about which axis it is rotating, it will not change. Okay, so now this means that you can rotate about x-axis, y-axis, or z-axis, and you'll get the corresponding rotation matrix. Okay, now you can rotate about more than one axis. For example, we have a coordinate system like this. Let me say this is my x, y, and z. So this is my x, that's my y, and that's my z of frame A. So the first rotation that I'm going to give, maybe there's another frame which is frame B. The frame B is rotated about z-axis by an angle alpha. Okay, so frame B is rotated by an angle alpha about z-axis. Okay, so what happens to frame B? This fellow comes here. This is my angle alpha, x dashed is here, and y dashed is there. Okay, now I have rotated about z-axis. Now I can rotate about some other axis. Now I'm going to rotate about maybe the x-axis. So let me rotate the second one. Frame B is rotated by an angle beta about x-axis. So I'm going to rotate about the fixed. Please note, in the first case, you don't have a choice because all the axes are the same. In the second case, because the axes have shifted, now I can rotate about this or I can rotate about this. Okay, so what we are going to rotate is, this is called the fixed angle rotation. And we are going to rotate always about the fixed angles, the fixed axis rotation, not fixed angle, sorry, fixed axis rotations. We are always going to rotate about the fixed axis. So my second rotation also will be about the fixed axis, which is my frame A. The fixed axis is frame A, always, the one that does not move. So second one we are rotating, so what will happen to, it will come here, x double dashed, this will become y double dashed, and this will become z double dashed. Now suppose I have a third rotation also. B is again rotated by some angle about y now. So B is again rotated by an angle gamma about y-axis. Fixed y again, it's always fixed angle. So about y it is rotating like this. So what will happen? This will go here, this will go here, and this will go there. Now I'm saying that there is a point here P expressed in frame B. It has coordinates u, v, w, and this point is the same point when it is expressed in frame A, which is not moving, it is XYZ. Now you find what is the relation between XYZ and UVW. So there has been 3 rotations, and we know the independent rotation matrices for each case. When it's rotating about Z or X or Y, it will be respectively these matrices, X, Y, or Z. So you know the matrices. Now the question is, if you want the combined rotation matrix, you have to multiply all of them. Okay, but what is the order of multiplication? That's important. So we had alpha, then we have beta, then we had gamma. But when you're multiplying it, what will happen is your rotation matrix will be reversed in order. So this is going to become R, Y, gamma into R, X, beta into R, alpha, Z, alpha. So this is what we call pre-multiplying the matrices. So please note that the matrices have been pre-multiplied. That means the order in which we carried out the rotation, they have been reversed. Okay, so this was 1, this was 1, then 2, then 3. But when we are multiplying, it is reversed. We are reversing the order, and this is called pre-multiplying. Okay, please note this very carefully, that you're pre-multiplying when you're multiplying when there's a rotation about the fixed axis. Okay, so we pre-multiply the matrices. Now there is also, so this is called the fixed axis rotation. We can also have the Euler angles, or rotations about the rotated frame. Okay, so the previous one is also called fixed axis rotation. This is also sometimes called roll pitch yaw. This can also be called roll pitch yaw system of rotation, but it is always about the fixed axis. Please note, and you always pre-multiply. Okay, now there can also be rotations about the rotated axis, and these are basically called the Euler angles. For example, we have X, Y, Z. This is my Z axis, X axis, Y axis. So here we can rotate about this is also called Z, Y, X axis system of rotation. In the previous case, it is sometimes called X, Y, Z. So you rotate about X, then about Y, then about Z. Although I did it the other way, doesn't matter. But we basically pre-multiply matrices when you're using a fixed axis rotation system. In the Euler angle case, I'm rotating about the rotated system. Please note that carefully. So the first rotation is about Z. It comes here. So that's my frame B. This is my frame A. So it comes here. Okay, so this is my X dash and X double dashed. In the next rotation, what I'm going to do is I'm going to rotate about the rotated frame. So it was Z, Y. I will rotate about the rotated Y frame. This is my Y. Okay, so I'm rotating about the rotated frame. Now what will happen? Now it's a little difficult to visualize. So what will happen? This will go here, X double dash, and Z will come here. Okay, and then I'm going to rotate about it was Z, Y, and then X. Now where is X? X is here, but the rotated X. Okay, I'm rotating here now. So this is gone here and that's gone there. Now if you have a point P which has in frame B, which has coordinates U, V, W. So this is my U, V, and W, and the same point in frame A will be X, Y, Z. So now we want to know what is the relation between these two. The rotated point, the coordinates of the point expressed in the rotated system in frame B to that of frame A. Now in this particular case, you do not pre-multiply, but you post-multiply. That means there is no change in order of multiplying. Okay, that means what was the first one we took? We took a rotation about Z, right? So it was R, Z by an angle, let's say alpha. Then I took a rotation of R, Y, beta, and R, X, alpha, beta, let's say gamma. But the rotation matrix, combined rotation matrix, okay, will be equal to R, Z, alpha, R, Y, beta, and R, X, gamma. Okay, that means the order in which we multiply did not change. In the previous case, I reversed the order. So please note. Now we do not follow this in the robotics. Normally, we do not follow this. Do not follow because it is difficult to visualize. It's like saying that you are sitting on a rotated system and you're rotating yourself and you're looking at the reference frame. In the previous case, we follow this. So we follow this system. Why? Because you are sitting on the fixed frame and you're watching the rotated frame. Now it's much easier to visualize. Okay, so you are sitting here. You can imagine yourself on the fixed frame. So you're not moving. You're looking at the rotated frame. and here you pre-multiply, and it's easy to follow. So we follow this system when we do our transformations. Okay, please note that. In this case, you are sitting on a rotated frame and you're watching the reference frame on a frame which is moving. Now that is difficult to visualize actually. So we do not follow, but it's possible. Okay, the point why I'm explaining this is that it is possible. And just remember that if you're using the rotated angle system, then you post multiply. If you're using the fixed angle system, you pre-multiply. Okay. Now we talked about rotation matrices. Now let's move on to translation. So we have seen that there are two operators. One is the rotation operator and the other is a translation operator. Now let's assume that, now let's look at this, there is a fixed frame A, which is X, Y, and Z. Now initially another frame B was coincident. Coincident means what? The origins were the same and the axis, there was no angle between them. It was the same. Now I rotate that frame B by some angle. You can imagine that I'm rotating, let me change the color. So you can imagine that I'm rotating the frame B with some angle like that. Okay, it has come here, and then I'm translating it. Okay, so what did I do? I rotated that frame B and I translated the frame B. So it's gone there now. Okay, so B has gone there now. So it's my X dashed, that's my Y dashed, and that's my Z dashed. Okay. So this includes a rotation and a translation also. So this is including a rotation plus number 2, there is a translation between origins. Okay, now there is a point in frame B. Let's talk about this point as this point in frame B is called P. Let's call it UVW. Now the same point in the point is P. So AP is X, Y, and Z. Now I want to know what is the relation between the coordinate of the point P expressed in frame B, which is this vector, okay, which is X, UVW. UVW means what? UVW means extension on this X, Y, and Z. That's the distance UVW. It's on frame B. Now I want to know what is the coordinate of this point, which is expressed as UVW in frame B in terms of frame A, because I'm interested in the reference frame which is not moving. Okay, so now I want to find AP, which means now in terms of vector diagram, it is this, and that is my vector here. So that is AP. I want to know what is AP. Okay, this one is BP. Okay, now what is this vector? This is the distance between the origins, and we write it as APB ORG. Okay, so the point is P. It's a distance between the origins of two frames A and B. That's how it's written as APB ORG. Okay. Now if we write the vector closed loop equation, what do we get here? AP is equal to APB ORG plus BP. Okay, so AP is equal to APB ORG, that is this distance, plus that distance, plus this one. Now please note that you cannot add vectors in frames which are rotated with respect to each other. Okay, so you can add vectors between frames which are not rotated, which don't have an angle between them. Okay, but not in this particular case where there is an angle between frame A and frame B now. So if you want to align frame A and frame B together, what you have to do, you have to put a rotation matrix here. If I put a rotation matrix here, what will happen is frame B will get aligned with frame A now. Now you can add the vectors. Okay, so now if I write in matrix form, what was AP? It was X, Y, Z, and 1, and this is equal to this matrix has 4 parts. This is my BP, U, V, W, and 1. Okay, this is the distance between the origins, del X, del Y, and del Z. This is 0, 0, 0, 1, and this is the rotation matrix, which is the rotation matrix, which is 3 by 3 matrix here. Okay, so if it was a rotation about Z axis, then this fellow is going to become cos theta minus sin theta cos theta 0, 0, 1, 0, 0. Okay, so this matrix is called this is a 4 by 4 matrix, and this is called the homogeneous transformation matrix. Now what does this mean? This part, let me explain the 4 parts of this matrix. This part is the rotation matrix. So this is an R 3 by 3, and this is called the rotation matrix, the same matrix that we just saw. Okay, this is called the translation between origins. Okay, translation between origins. That means del x, del y, del z is the distance between the origins in the x, y, and z direction. So this is my del x, that is my del y, and del z in the z is in the z direction. Okay, that is in the z direction. Okay, this is the meaning of del x, del y, and del z. It means the distance between the origins of the frames A and B. Translation between origins of A and B. Okay, this is the meaning. This is always 0, 0, 0, and this is always 1. This is called scale. This is called perspective. Okay, and this is my coordinates in frame A, AP, and this is my coordinate in frame B, which is BP. Okay, so what we see here is that we can, this matrix, the 4x4 matrix, considers the rotation and the translation between two frames. Okay, now this is the homogeneous transformation matrix, which can relate the coordinate of a point in a rotated and translated frame to that of the reference frame. Okay, it consists of the rotation matrix, it consists of the translation part between the, or the distance between the origins. This part is always 0, 0, 0, and this is always 1. Okay, please note that this is a 4x4 matrix, and this is basically a homogeneous transformation matrix. I have also derived it, so you can follow how it was derived. Okay, so now we understand the rotation matrix. Let me just go back a little bit here and try and explain what is the meaning. So the meaning of this matrix z theta is that it is like you're giving the coordinate of a point in frame B, and then the coordinate of the point in frame B is being converted to frame A. Okay, so we're going from frame B to frame A. Okay, please note that. Now let's do a few problems. So these are the homogeneous transformation matrix will allow us to go from one frame to another frame. So now let me look at the bigger picture here. So we have one frame, we have a serial link manipulator like this. Okay, and we are assigning frames. So we are assigning frames here. So Z0, Z1, then Z2, Z3, and there's a Z4 there. I'm putting X0 here, X1, X2, X3, okay, and X4 there. Now I can find the transformation matrix from frame 4 T0 to 4, means from fourth is the last one here, right? From 4 to 0. So from 4 I'll come to 3, which means how do I come? I go from 0 to 1, okay, then from 1 to 2, 2 to 3, and 3 to 4. So these are homogeneous transformation matrices. So if I multiply them out, I'll get the final matrix, which is going to relate frame 4 to frame 0. Each of this gives the relation between two frames, adjacent frames. And if I multiply them out in this order, we do not pre-multiply, we post-multiply, because you're in 4x4 homogeneous space now. Okay. So getting the homogeneous transformation matrix, we can find the relation between two frames in space, and then we multiply all of them together. We can go from any frame to any other frame. Here I've gone from the end effector to the base frame. Base frame is not moving, so we need to express that in the base frame. Okay. So now I hope you understand the effect of the requirement for the homogeneous transformation matrix. Okay. So now let me try and explain this a little bit more, why this is required. As we go along, it will become clearer, but just to give you a very brief insight into the requirement for all this, say for example here, suppose you want to pick up an object which is kept on a table. Okay, so this is an object which is kept on the table. Okay. Now this is 0, 0, 0, which is fixed space. Now this will have some coordinate. I want to catch that, so I need to know that vector. Okay, or rather I need to know this vector. So from here I need to, let me change the color and say from here I'm going here, then from here I'm going there. Okay, let's call this base, let's call this table, let's call this part. Okay, so that is one line. The other is from here I need this vector. This vector, how do I get? I get from here to here, then here to here, here to here, here to here, means this one. Okay, so I know this vector. I also know this vector. Which vector don't I know? I don't know this vector. I do not know this vector. Okay, so this is the one that I don't know. So let me call this end effector. This is my end effector or tool. So I do not know that vector. So how do I get it? So if you look at the two vector closed loops, one loop here, another loop here. Okay, so basically we can write our equation as from one loop is b to e. One loop is in terms of the vector equations b to e, and this is e to b. So here and here, that's one vector loop, is equal to, these are transformation matrices T. Okay, now the other loop is on the other side, just going from here to here and here to here. Okay, so this is equal to T b to t into t t to p. Okay, so this is one loop and this is another loop, and it's a closed loop. What do I want to find? I want to find e to p. I need this fellow. So how do I get it? So t e to p is equal to, I'll take this one on the other side, so t b to e inverse, okay, into bt into t into t tp into t. Okay, so I'm getting this vector now, and that is what the controller needs to take the end effector from this point to that point. Okay, and these are all 4x4 matrices, so the controller actually knows what is the orientation required to change and the distance between the origins. Okay, so this is giving you an idea of what is the use of this. Okay, let's move on and do a few problems now. Now we need to do a few problems so that it becomes clear what we are trying to do here. Okay, so as I said in the previous class, please do definitely derive this matrix by yourself. Okay, this matrix you should be able to derive by yourself. Okay, there is nothing difficult about it. So please derive this matrix. Please derive this. We are normally rotating about z-axis only, so don't have to worry about the others. If you know just this matrix, it's a very simple matrix: cos minus sine, sine cos, and you can derive it in just a matter of few seconds. So if you derive it once, you're not going to forget it, and there is no need to by heart. Okay, so this I would strongly suggest that you derive it by yourself and also derive this one, that is the transformation matrix. Okay, the translation and rotation together. Again, if you derive it, there is absolutely no problem. You don't have to remember it. There's nothing to remember here. Okay, now an interesting point of this which I forgot, this is just to explain what is the need for this transformation matrices. Okay, now let us look at the inverse of the rotation matrix, which I just explained. Inverse of rotation matrix and homogeneous transformation matrix. Okay, homogeneous transformation matrix. So we said that the rotation matrix, which is given by rz theta, which is equal to cos minus sine, sine cos 0, 0, 1. This one is a proper orthonormal matrix. Okay, and hence the inverse of this is equal to R transpose. Okay, so R inverse Z theta is equal to cos sine 0, cos minus sine cos 0, and this is 0, 0, 1. Okay, so the inverse is equal to the transpose. Please remember that. The other is, what is the inverse of the homogeneous transformation matrix? Okay, I want to know the inverse of this also. Why? Because you may be given BP, the coordinate of a point in a rotated system, and you may need to find AP. You can also be given AP and you may have to find VP. Then you have to go in the other direction. Okay, so what I'm trying to explain here is that AP is equal to the rotation matrix Z theta into BP. So I can give you BP and ask you to find what is AP. Or we can give you AP and ask you to find BP. So what is BP? BP is equal to RZ theta inverse into AP. Both sides is fine, right? Similarly, in the case of homogeneous transformation matrix, we are giving you AP is equal to the matrix T, A to B into BP. I can ask you to find BP, and this will become T inverse into AP. Please note that this inverse is not equal to transpose. Okay, please note this carefully. Okay, this doesn't apply. Okay, in the case of rotation matrix, it is equal. Homogeneous transformation matrix, they are not equal. They are not. The inverse is not the transpose. So what is the inverse? So the inverse of the T matrix is given by This part remains as 0, 0, 0 and 1. This part, the rotation becomes the inverse, which is equal to transpose. Okay, so that is easy. And this one becomes minus of r transpose into del x, del y, del z. Please note that. You can prove it very easily. So AP is equal to APB ORG plus R A to B BP. So I want to find what is BP. So to do that, what do I do? BP is equal to RB inverse into APB ORG minus AP. So I take this side, it becomes AP minus APB, I wrote it the other way around. So this is equal to AP minus APB ORG. Okay, and then you take the inverse of this on this side. So this is equal to BP. So what is this equal to? This is equal to R inverse. Inverse is equal to transpose, which comes here, into AP minus of ABP ORG, which is given here. Okay, so we can prove this also very easily this way, and this is what the answer is. Okay, now this is always 0, 0, 0 and this is always 1 in robotics. Okay, so let's look at a few problems before we proceed further. Problems will make it clearer. So let's have an example here. So we have a frame B is rotated by 30 degrees about z-axis of frame A. Okay, so frame B is rotated. So we have a frame, let me draw it and explain. So we have X, Y and Z. This is my frame A. So we have another frame B which has been rotated by an angle 30 degrees about the z-axis like this. Okay, and this is my frame B now. So this is X dash, Y dash. Now we are told that the coordinate of a point in BP is equal to, so there is a point here P expressed in frame B. Its coordinate is equal to 2, 2, 2. So this is equal to 2, 2 and 2. What is the meaning of that? This means projection here is 2, projection here is 2, and on the Z side also it is 2 on frame B. We are asked to find what is AP. Find AP. Okay, so I hope the question is clear. We have a point P expressed in frame B. It has coordinates 2, 2, 2. I want to find its coordinates in frame A. Frame A is the reference frame. How do I solve the problem? AP is equal to, this is rotated by 30 degrees about z-axis. So this is equal to cos 30 minus sin 30, sin 30 cos 30, 0, 0, 1, 0, 0, and this is equal to 2, 2, 2. This is my BP. This is equal to X, Y and Z. Okay, so AP is equal to R into RZ theta into BP. That's how I got it. So what we can do, it's very easy. You can find out, so very easily you can find out what is the values of cos 30 and sin 30. So we can write this as 0.86 minus 0.5 and 0. This is 0.5 and 0.86, 0, 0, 0, 1, and this is given by 2, 2, 2. So you can multiply this X, Y, Z. You can multiply this out. So X, Y, Z is equal to, you can multiply it out very quickly and get the answer is 0.72, 2.72, and this is 2. Okay. So you saw that there was no change in the Z axis. Please note that, because we are rotating about Z. Okay. Now the frame B was rotated and it had a coordinate BP was 2, 2, 2. And we were given this, we were asked to find what is AP. Now suppose I give you AP. I said this is AP now. Suppose I give you AP now and I say you find BP. Okay, so exactly the same problem. I'm going to give you AP now. Now AP is this, right? So if I give you AP, so given the same, given R Z theta, okay, and AP, what did we get AP as? We found AP to be equal to 0.72, 2.722. This is what we found AP to be. Now you find BP. So it was B was rotated by 30 degrees about z-axis. In the previous example, I gave you BP, which was 222. Okay, I gave you, and I said find AP. So what did we do? We found the rotation matrix, which was given by this. Okay, then I multiplied and I got this, which is my AP now. Now I'm saying that I'm giving you AP for the same rotation. You tell me what is BP now. Okay, so how do we do that? AP is equal to RZ30 into BP. Okay, now I want to find what is BP now. Okay, so BP is equal to, implies BP is equal to RZ30 inverse, which is transpose, into AP, and AP is given here. Okay, so now if I look at the inverse of the previous matrix, then what we get is BP is equal to R transpose. So what we get is the transpose of the matrix cos 30, okay, sin 30 minus sin 30 cos 30, 0, 0, 1. This matrix is this matrix. Okay, inverse is equal to transpose, and AP has been given to be equal to 0.72, 2.72 and 2. Okay, so what I can do is I can write down the values. BP is equal to 0.86, 0.50 minus 0.5, 0.86, 0, 0, 0, 1, and I put the values here, 72, 2.72, 2. When I multiply it out, what do I get? BP is equal to 1.98. There is some approximation in terms of sine and cos, so we get this, and this is exactly what was BP, right? So what was BP? BP was 222, right? So from BP I got AP. Now I'm giving you AP, this value, and I'm saying you find what is BP. So we multiply it with the transpose of the rotation matrix and we get back exactly the same value. It was 222, but there is some approximation here. So it's 1.99, 1.99. Okay, because sine and cos are there, so there will be some approximation errors. Okay, so this shows you how to go from AP to BP or BP to AP using the rotation matrix. Next, let's look at the homogeneous transformation matrix. So a frame B, let's say, is rotated by, so this is a frame B. So let's look at the second problem, which is a frame B is rotated by 45 degrees about z-axis. Of frame A, and then it is translated by 555 units in the x, y, z directions of A, in the x, y, and z directions of A. Okay, so let's try and understand this. So we have a frame A. This is my frame A. So this is my frame A. Y and Z. Now there's a frame B. Now this frame B is rotated by 45 degrees like this. Okay, frame B is rotated by 45 degrees, and about the z-axis, sorry, so this is rotated by 45 degrees about the z-axis. So it is, let me mark this as z, so it will become easier to understand. This is x, y, and z. So 45 degrees, so this fellow is here, 45 degrees, it is here. Okay, now it is rotated by 45 degrees, okay, about z-axis of A, and translated, and then it has been translated by distances of 555 units in the x, y, z directions of A. So it has been moved here now. Okay, so now the frame has been moved in this direction here. Okay, so my frame B has gone there now, and this is the distance there is 5, 5, and 5 units in the x, y, z directions of A. Okay, now we are told that there is a point P here which has coordinates. Let's give it some coordinates. Let's again say it is 2, 2, 2. So PB is equal to 2, 2 and 2. Okay, these are the coordinates that and you're asked to find what is AP. Sorry. So P in terms of B is given this. Now you find this coordinate. Okay. Now given BP, the coordinate of the point P in frame B is equal to 2 and 2 and 2 units, find AP. This question is very clear, I think. So now we are required to find, so AP is equal to the homogeneous transformation matrix A to B BP. Okay, and this is equal to AP is equal to X, Y, Z1. This is a 4x4 matrix, so it is going to become cos 45 minus sin 45 0, sin 45 cos 45 0 1 here. So this is one part of it, this is 0 0 0, this is 1, and this is equal to 5 5 5, and this is equal to 2 2 and 2. Okay, so this part is the rotation part, which is equal to RZ 45. This is the translation part, so del X del Y del Z, which is the distance between the origins. So this is distance between origins. Okay, and this is BP. Okay, which is given. So now multiply it out. So let's put in the values. So once you put in the values, what we get is AP is equal to cos 45 is 0.7 minus 0.7 0.5. This is equal to 0.7 0.705. This is 0001. This is 000, and this is 1. And what was BP? BP is given as 2 2 2 and 1. So when I multiply it out, I get my answer as 5. So this is 5, this is 7.8, this is 7, and that is 1. Okay, so what is AP? The coordinates of the point AP. So AP is equal to 5, 7.8 and 7. Okay, so we have got the coordinates of the point P, which was expressed in frame B in terms of frame A, which is the reference frame. Okay, so this is a very simple procedure. Once you understand the rotation and the homogeneous transformation matrices, it's very, very simple. It's just a question of putting in numbers and getting the values. Okay, so now let's look at the inverse of this. Now in the same problem, suppose we have RZ45. So B is moved by rotated by 45 degrees about z-axis and translated by 555 units in XYZ directions of A. Okay, the same as the previous case, exactly the same. So your frame B, which has been rotated by angle 45 degrees and translated by 555 units in the XYZ directions of A. But in this case now, suppose I give you AP, the coordinate of a point P in frame A is equal to 5, 7.8 and 7. Okay, that means I'm giving you, this is AP, I'm giving you AP, and I'm saying now you find BP. Okay, just the reverse of this, or rather the inverse of this problem. Okay, so now how do we find? We need to find what is, so AP, we know AP is equal to T A to P BP, which implies that BP is equal to T A to B inverse into AP. Okay, so what is T inverse? T inverse, let's go back and just look at what was T inverse. T inverse was equal to this matrix, so this T inverse. So this part is the rotation matrix inverse, which is the transpose. Okay, and this is minus of RT into del X del Y del Z. Okay, this is 0 0 0, this is 1. So I need to find this and this. So what we do is I take the rotation matrix which we got with the homogeneous matrix which we got was this one. Okay, this is T A to B. I want to find its inverse. So how do I find? I take this part and I invert it. So I take this part, the rotation matrix, and do its inverse. So R inverse of that part. So T A to B inverse is equal to this. Then this part I'm going to do minus R transpose into del X, del Y, del Z. This is always 0, 0, 0, and this is 1. That is the inverse matrix which I require. So if I invert it, what do we get is here I'm inverting it. Let me write it this way so there is lesser confusion. AP is equal to cos 45. We had just written down cos 45 is 0.7. Now let me write it, otherwise it may cause a little confusion. Cos 45 minus sin 45, sin 45, cos 45. This is 0, 0, 1, 0, 0. Distance moved is 5, 5, 5, 1, 0, 0, 0. Okay, this was the matrix into BP, which was this is BP, right? Now I'm giving you AP and I want to find what is BP. So find BP. BP is equal to inverse of this now then. So how do I find the inverse of that? So BP is equal to inverse of this matrix. What is the inverse of that? This part is going to, let me change the color. So this part is going to become the transpose, which is equal to 0.7, 0.7, 0. This is the rotation part minus 0.7. This is 0.70. This is 0.01. This is the rotation part. So I have taken the inverse of this. Okay. So this is my T matrix. This is T inverse. So I'm taking the transpose of this. So this will become R transpose, this matrix, which is given here. This is 0, 0, 0. That's always 1. So that's one part. The second part is I have to take minus of R transpose, okay, into del X, del Y, del Z. How do I compute this? I compute this simply by taking the R transpose, which is here. So 0.7, 0. So let me write it down. 0.7, 0.70. Then it is minus 0.7, 0.7, 0, 0, 0, 1. Okay, into del X, del Y, del Z, minus of that. So it's minus 5, minus 5, minus 5. Okay, I hope you understand what we did. Okay, so this part is given here. So what is the numbers that comes out? Minus 7, 0, and 5. Okay, this comes out to be minus 7, 0, and 5. Now we are given the coordinates of the point AP. So what is the coordinates of the point AP? It is equal to 5, 7.8, and 7. This is 1, right? So this is what we are, this is my AP now. So if you multiply it out, what we'll be getting is BP is equal to 1.96, 1.97 actually, 1.97, 1.97, and 2. So we are getting back BP. So we said in the previous case that BP was equal to, this was BP, which was equal to 2, 2, 2. Okay, and this was AP. So I now gave you AP and I said you find BP. So I put input AP here. This is my AP. Okay, multiplied with the inverse of the transformation matrix, and I got BP. BP is equal to 1.97, 1.972. Again, this is an approximation, numerical error because of sin and cos. But then we have gone from BP to AP and AP to BP. Okay, by using the matrices. Okay, so I hope these two problems will clarify. We have one small problem which we can look at in terms of combined rotation matrix, combined roll pitch, the fixed angle rotation, and then okay, so let's look at this matrix, this problem here. So the problem here is we are having 3 rotations. You can have 2 rotations, you can have 3 rotations, you can have 10 rotations about fixed angle rotation. Okay, it doesn't matter. So fixed angle rotations, we have a frame B. So a frame, the color is, so frame is rotated by 30 degrees about x of A, then by 60 degrees about y of B, and then 30 degrees about z of A. Okay, so first it's rotated about the x-axis, then it's rotated about the y-axis, and then about the z-axis of A. So 30 degrees, 60 degrees, and then 30 degrees again. So the order of rotation was the first rotation was x 30 degrees about x, then the second one was 60 degrees about y, and then the third one was 30 degrees about z. Okay, now this is about z of A. So this means rotations are all about please note that this is A. I might have made a mistake there. So these rotations are all about rotations of A. So there is a fixed angle rotation. So 30 degrees about x of A, then by 60 degrees about y of A, and then 30 degrees about z of A. So this is a fixed angle rotation. Okay. So now we can find the respective rotation matrices. So this is going to become Rx30, this will become Ry60, and this will become Rz30. Now the question is, what is the order of rotation? Okay, now because it's a fixed angle rotation, we are going to pre-multiply. Okay, which means that I will reverse the order now. So I'm going to make this matrices in this order: 30 cross Ry60 cross Rx30. Okay, and we can write them down. So my combined rotation matrix, the combined matrix is going to become equal to cos 30 minus sin 30. So sin 30 cos 30 0 0 1 0 0. This is equal to cos 60. This is a rotation about a y-axis, so let me write down the proper matrix first. Minus sin 60, so this is sin 60, this is cos 60, and then we have rotation about the x-axis by an angle of 30 degrees. So this is 1 0 0 0 0. So cos 30 minus sin 30 cos 30. Okay, so it's only a question of putting in the values now. So this combined rotation matrix is equal to, so the values if I write down is 0.86 minus 0.5, this is 0, this is 0.5, 0.86, 0, 0, 0, 1, this is equal to 0.5, 0, 0.86, 0, 1, 0, minus 0.86, 0, 0.5, and 1, 0, 0, 0, 0, 0.86, minus 0.5, 0.5, 0.86. Okay, now if you multiply it out, the combined matrix comes out to be equal to 0.43 minus 0.06, 0.88, 0.25, 0.95, minus 0.06, minus 0.86, 0.25, and this is 0.43. This is a combined rotation matrix. Okay, so we were given okay, I did not complete the question maybe about ZA. So if you are given BP is equal to 1, 1, and 1, we are said find AP. Okay, so now AP is equal to the combined matrix R into BP, and so AP is equal to this matrix 0.43 minus 0.06, 0.88, 0.25, then it is 0.95 minus 0.06, 0.86, 0.25, and 0.43 into BP, which is given as 111. So when I multiply it out, I get AP is equal to 1.25, 1.14, and minus 0.18. Okay, so this gives you an idea of how we use this matrices, the rotation matrix and the homogeneous transformation matrix, in terms of in terms of computing the coordinates of a point expressed either in, if it's given in B, you can find it in A. If you're finding it in A, then you can find it in B. Okay, so today we looked at how to derive the rotation matrices and the homogeneous transformation matrices. Then we solved a couple of problems which actually showed us how to use these matrices in computing. If you're given coordinates of a point in either A or B, how to convert it to the reference frame. Okay, now we also talked about multiple rotations. Okay, so please note that in multiple rotations you have to worry about you have to pre-multiply in case of fixed angle rotations. Okay, so we'll stop here today and we'll continue in the next class. Please do practice these problems. It's very easy. There are only two matrices to remember, so please practice them properly, otherwise you tend to forget, and once you practice it becomes very clear that how these rotation matrices are being used. In robotics, we must know very clearly what the homogeneous transformation matrix means and how to use it. Otherwise, it's no point in studying robotics, and we will not be able to go into the future topics, further topics like inverse kinematics, forward kinematics, Jacobians, etc. Okay, so we stop here today. Thank you.